So welcome to the IGLUNA project show. IGLUNA is an international student platform coordinated by Space Innovation and bringing together the student teams from all over the world to develop the technologies relevant for the future of space exploration. Our guest today is the team P04 from Warsaw, and they will be telling you about their experiment to terraform the lunar soil to be able to grow the plants on the moon. We will start with a short video about the project.
Hi, Sample Tutim here. We are students from Warsaw University of Technology. We are going to walk you through our journey to IGLUNA 2021 field campaign. Our project aims to grow edible plants on terraformed lunar soil in an autonomous module. This project may revolutionize plant cultivation in space and on Earth. I am a part of biological team which conducted terraforming experiment. Our goal is to create an easy technology of terraforming which will change the physical and chemical properties of lunar soil regolith simulant. That is why our team is divided into two groups, research of bacteria and research of plants. To make this possible, we had to find the best microbial candidate to suit our preferences. After research, we decided to use Rhodella oensidensis, Cryptococcus albidus and Rhodopseudomonas palustris.
We decided to use this organism because they have low life requirements and they produce various substances which are beneficial for our process. We obtained specific strains and checked how long do they grow and if they are aggressive towards each other. We did not find any antagonistic reactions, so our research of bacteria ended there. So now we can move to the research group of plants, and we will tell you a bit about how we selected plants for our experiments.
We would like to tell you a bit about how we selected plants for our experiment. We had to search for plants that are able to grow on lunar soil, which is soil with alkaline pH. Plants prefer acidic or neutral soil, so we had to compromise on this. These plants should also be undemanding to the conditions and nutrients in soil. They should sprout within 8 days. In this case, in a short period of time, we can evaluate the result of our experiment. We have chosen small plants because we don't have a lot of space in our module. Chosen plants also should be edible and contain a lot of nutrients. They have the criteria such as humidity, need for light, germination and growth temperature should be within optimal limits.
We selected 4 plant species that would be able to grow in the described conditions, and that would be lettuce, cress, rocket and endive. And in order to control the factor that could make our plants not grow in the module, we decided to plant our species in different conditions. And the first option would be to plant the plants in normal soil and without recirculation. The second option would be to plant the plants in terraformed soil, simulating lunar soil, also without recirculation. The third option would be to plant the plants in normal soil, but with recirculation. And our key option, our final option, would be to plant the plants in terraformed soil, simulating lunar soil, and with recirculation. And that way it will be easier for us to find the source of failure if some factor fails. And thanks to that, we will be able to modify our experiment and to adapt it to the needs of the plants and to the requirements of the module.
After all research, we begin our small sample experiment. We sterilized soil, organic compounds, water, and created a simulation of model on smaller scale. We put everything in the glass jar, closed it tightly, and we put it under UV lamps. After some time, we opened and checked how plants did grow, measured the amount of sprouts, and evaluated how they look. We also observed the terraformed soil under the microscope. Finally, we compared the results of our experiment with standard soil with the same pH level and with lunar soil regolith without bacteria. In conclusion, we think that our project has huge potential, especially when it comes to increasing a number of microorganisms.
Now we are going to talk you through the mechanical part of our experiment. In order to sustain sterile conditions and to prevent any contaminations, we have built an autonomous module capable of sustaining plants' life.
Our module is built from aluminium profiles and aluminium panels. To make it watertight, we covered all holes and connections with glue and silicone. The top cover is screwed on and we enforce it with a gum gasket so that no water may leak inside.
A layer of isolation is placed on the exterior to help sustain the optimal temperature inside. We've covered the module with a silver heat blanket that may reflect heat, and also we've put a radiator on the top that dissipates heat. All of this was done to make sure that the module does not overheat.
This is the brain of the whole operation, our main onboard computer. It may seem small, but it plays a very important role in our experiment. It monitors the environment inside the module and controls lamps and heater.
It also reads data from all sensors. In this experiment, we are using 4 types of sensors. The temperature sensor, very important for heat control. A sensor that measures intensity of red, green, and blue light, which allows us to determine if lamps provide enough energy for the plants to grow.
We monitor CO2 levels inside, from which we may calculate how much energy was used by plants. We also place a camera inside that will allow us to inspect our plants in real time.
All this collected data is put online where we can keep our eyes on the current sensor values as well as leave it for further analysis. Also, we're able to remotely change automatic control parameters of the heater and manually switch the lamps.
This concludes the tour of our self-sustaining autonomous plants growing module.
I hope you enjoyed our presentation. If you have any questions, don't hesitate to contact us at our Facebook page or come talk to us at the Werkhuishuis Museum. Thank you. Bye-bye.
Welcome back to Pilatus. I hope that you enjoyed the video, and now it's time for the live Q&A session with the team. So let's see if we have any question for the team. Maybe I will start with the question. So I see that you're holding an object here in your hands. Could you maybe explain again to our viewers what it is and anything that you would like to explain about it?
This is the terraformed lunar soil that we are planting our plants on. And Conrad, please tell more about the chemical composition of it.
So this lunar soil regolith is mostly silicon dioxide. It's really close to the normal sand that we can have on the deserts. However, it's different on chromium and other oxides which are quite harmful for the organism, and our goal is to make them less harmful for them and also to grow plants.
I see, thank you very much. So is it a new experiment? Do you have already any information on the research that has been done on this topic?
So there is little to no previous experiments considering such complexity as terraforming lunar soil regolith. So for now we can say that we are the first one who speak loudly about this type of experiment. Maybe some other teams are working, but we have no contact with them, unfortunately.
I see, thank you very much. And in general, do you have already some ideas how to develop further your project?
So for a biotechnological experiment, we'll look closely about physical properties of this regolith to make it more available for the plants. Also, we have quite challenge with water because in some cases water goes up with our regolith, so we need to resolve it. However, we have some few ideas how to cope with it. Maybe you will talk about the technical part.
We're planning to expand our modules to grow bigger plants and maybe make some other multiply the modules so that we can plant different plants at the same time and check the results at the same time.
Thank you very much. So given the idea of terraforming the lunar soil, can you still think about applications for Earth?
So for Earth, we think about fertilizing Sahara Desert, for example. Also, the unfertile soil, we can create a procedure to refertilize it. Also, the limitation is in our head, like we can use it anywhere we want. If we want to plant some vegetables on Arctica, sure, why not? We are analyzing for now what is capable or what is not, but we believe that this experiment has huge potential right now.
Great. Well, that's really nice to see you're so motivated about your project. So during this year, what was your biggest challenge with the project?
Probably access to laboratories due to COVID. The COVID restrictions hit us really hard, especially the biological part. We couldn't access the clean rooms, but it was a challenge, but we managed, and we have the terraformed soil right here with us, and we have some promising results so far.
Great, thank you very much, and it's really nice to see your project here on Pilatus. So somebody is asking, how difficult is the terraforming process?
For now, as we call it, terraforming process is on the concept phase. Right now we are checking exactly what's happening on the soil more empirically. After that we'll do some equations to optimize it. It's really difficult because our lunar soil regolith has a lot of particles, which in some cases, when other groups tried just to plant some vegetables and fertilize it, they were removing a lot of parts, and we have like the best available regolith right now, and has everything in it. So there's some glass particles which are really difficult for plants to cope with, and also for microorganisms. For now we just looking what's happening and we try to adapt, but for now it's quite difficult road, as I would say.
Great, I see. And maybe staying on the topic, how is your project here on Pilatus going on? Would you like to say a few words? What was happening in the past few days?
So for the past few days we are analyzing data about temperature, soil moisture. We have the live view from the camera. However, we are not able to see everything as good as we would like to. We think that there is some plants on our regolith and on the soil, but we cannot say it for 100%.
Yes, everything is running. The remote control is actually really good, and we have the live view from the module inside, so we're really happy with how it turned out.
Thank you very much. I see that somebody is asking, how much soil do you need to create to grow one plant?
It's really hard to say because the most important part of the terraforming project is to terraform it. Amount is not such a concern. It depends on the thing where you want to grow it. For now we are using small boxes, so it's like about 300 grams of the terraform simulant, but it depends on the thing you put this soil on. So for now we are more concerned about terraforming part than for the amount of terraformed soil.
Thank you very much. I see that there is a related question. Have you evaluated how much surface you would need to feed a group of astronauts on the moon?
Right now, not, because as I said, it's a concept. Now we are doing everything from the scratch. We are looking more about the results, how terraform is going, how much time does it take to do it even. So this will be the calculation will be after the IGLUNA. And I think that's all what I can say for now, unfortunately.
Thank you very much. So still a lot of research ongoing. Great. There is a question, is it easy to produce your model on mass scale? And maybe also related to that, is it necessary to use exactly this model for the terraforming process?
Building up the module is really easy. It's just aluminium profiles and aluminium sheets. It's not difficult at any point. And sorry, what was the second question?
Is it necessary to use
this exact module? This exact module, probably yes, because the risk of contamination is really high, so we need to seal the box really good. But if we have another another module that can also provide this feature. I think it should work, but the ceiling part is really important, and also the control of the light and the temperature is a key factor here. So.
Also, the goal of the whole project is to plant vegetables outside of the habitat. That's why this module is necessary for it, because we want to reduce the space needed in habitat, or to give it to some more important thing than growing vegetables. Also, for example, our module can be also a gas plantation, like we can create nitrogen, oxygen, carbon dioxide, independent of the microorganisms which will be used on the module. So for now, we believe that we need to use both technologies together.
So you mentioned growing the vegetables, and somebody is actually asking what vegetables are the easiest to grow in this terraformed soil.
For now, the only positive result was watercress. However, we are checking rucola, lettuce and envy. We hope that this time they will grow correctly.
Thank you very much. Somebody is asking, could the microorganism be harmful in any way to the astronauts?
So we have chosen 3 microorganisms which are biosafety 1, which means they are completely safe for the astronauts. Of course, as biology goes, there is evolutionary stuff and it may be harmful, but for now there is no harm. Of course, every biological experiment needs to be watched carefully, but as we are for today, there is no need to be worried about.
Thank you very much, and I guess we'll hear more after the end of the experiment when we see the plants. So I think we do not have any further questions from the YouTube chat, but in case you would like still to add anything else to your experiment or your experience at the field campaign here in Lucerne.
I would like to say that it's a pleasure to be here and to talk to all the experts and other team members and other teams. It's a really nice environment, and we're really happy that we are here and we can perform our experiments and present it to a larger public. So thank you very much.
I would like to thank my whole team, because what we did was really tough. And I'm really proud of the results right now. Also, I would like to thank our university and our Faculty of Chemistry for believing in us from the beginning and allowing us to do such extraordinary projects, I would say. We hope that you enjoy our presentation and that you will see that sample 2 may go to moon one day.
Thank you very much indeed. Looking forward to see the future of your experiment. So from my side, I would like also to thank you for being here today and presenting your interesting project to all of our viewers. And to all the viewers, thank you for watching us and thank you for interesting questions in our YouTube chat. Don't miss our future IGLUNA project shows online on our YouTube channel, and have a nice day. Goodbye.